Combination compounds part 2. Let's start by refreshing this idea of isomers. There's a specific bunch that I want you to know, in particular the names. And to that extent, we're going to start first with the octahedral structure, the one where you have 6 ligands bound to the transition metal. If you have a complex where one of the ligands is different from the other 5, this particular complex, no matter where you put this X ligand, will be pretty much the same molecule, because all that you will have to do is rotate the molecule to get to wherever the position X is within the octahedral framework. So you only have one isomer here, so you don't really need to worry about anything else extra. But then when you start having combinations, right? So now we have two types of ligands present in the molecule, right? So we have 2 L's and 4 X's. Here you could actually have a set of isomers. On the one hand, if we focus on the L's, here we have them right next to each other, 90 degrees apart, separate from each other. This is what we call the cis isomer. But if the L ligands are now opposite of each other, this is what we call the trans isomer. And as long as all the other ligands are pretty much X, X, and X, this is a sufficient way of referring to these particular complexes. Now, needless to say, the cis and trans denomination is a prefix to the entire name of the complex. You will still need to name the complex, but you will precede it with either cis or trans if you have this type of framework, right? So 2 L's, 4 X's. If you have 3 L's and 3 X's, then you can actually end up drawing two types of isomers. You could draw the FAC isomer, which basically stands for facial, since the 3 ligands occupy, the 3 same kind of ligands occupy one face of the octahedral shape. And on the other hand, you could actually have the X's occupying one plane and the L's occupying a perpendicular plane in the structure, and both of them are in different planes altogether. This is what we call the mer isomer. And much like cis and trans, FAC and mer prefixes will precede the entire name of the molecule. Alright, now if you have 4 ligands, there's two possibilities. The complex could be square planar or it could be octahedral. In the case where the complex is square planar, if all the ligands are the same, then that's pretty much it. There's nothing you can do to change this molecule into anything else. If one of them is different from the others, here you also have another choice, because if you place X anywhere in the positions of the square planar shape, all you will need to do is just rotate it on its own axis to get to that structure from the previous one. So this only has one isomer. However, when you have 2 X's and 2 L's, here's where you get into a cis-trans situation, much like in the octahedral example. If the X ligands are next to each other, this is cis, 90 degrees apart from each other. If they are in opposite ends of the molecule, meaning that they are across from each other, this is what we call the trans isomers, and you will still need to utilize cis and trans as a prefix followed by the name of the structures when it comes down to these molecules. Now the tetrahedral structure, where you have 4 ligands, if you have all ligands be the same, there's no extra isomer. If you have one ligand be different from the other 3, you only have one isomer. If you have 2 ligands, so 2 X's and 2 L's, you also have just one isomer. No cis and trans for tetrahedrals. And of course, if you change one more L to X, you get back to this situation, right? So namely speaking, you don't have different isomers. The only time you have different isomers is if all 4 ligands are different from each other, in which case you are looking at stereoisomers, enantiomers to be most exact. Alright, so let's stop this particular introduction to isomers, something that you'll need to get familiar with and comfortable with in terms of solving problems in the future. Well, let's stop the video right here and we'll start talking about crystal field theory on the next video.